Welcome back to DCL 091. Before I get started, a little warning. My allergies will not let go, so I will be hesitating and muting the mic once in a while. That is simply because I don't want to cough in your face. Now, the next three videos are going to be about very simple mathematical concepts in radio and electronics. I'm assuming you have no background in radio. You have almost no background in mathematics. I pledge to teach all these concepts without dragging you into the weeds of higher mathematics, and I think that can easily be done. This time around, we're only going to talk about the sine wave and symmetric prefixes. Next time, we'll step it up a little bit, but don't be intimidated by what you see. I am confident I can teach these topics to anyone, even if you don't have much of a mathematical background. That last bullet point is where I hope to show you how you can look at a formula, not do any math, and yet learn from and be able to use the formula effectively. I'll show you those tricks again in the next video. The last episode is going to be a little deeper, but again, logs and dBs and wavelength are not that difficult. So I look forward to presenting those in the next few days. Let's start with the good old sine wave. You're probably a little bit familiar with the idea of direct current. Electrons flow toward the positive terminal of the battery. We call it direct current because nothing ever changes. What about alternating current, like sine waves? Well, stare at the battery, and what I'm going to do, let's pretend that I can swap the battery around really fast. So here we go. 1, 2, 3, go. Notice the current now, of course, is going in the other direction. So let's swap the battery again. Now the current's going back the other way. Let's swap the battery again. We call this alternating current. Alternating current is current that reverses direction periodically. Now, if you were to graph the current flow in the wire, when I did that, it would look a lot like this. Now, what you would say at this point is that this is a square wave for obvious reasons. Notice, just for a moment, that most of the time, here, and here, and here, etc., the current actually is not changing. It switches, but it's really not changing. For reasons I'll get into in a minute, square waves are really kind of a bad thing. Yes, you use square waves in digital logic, but in radio, we don't like square waves. We like something a little more gentle. The sine wave is a form of alternating current that periodically reverses, but it follows the trigonometric sine function. And don't worry about trigonometry, we're not going to do any. But if someone asks you, why do you call it a sine wave? Just tell them it follows the sine function from trig. And that'll usually solve their curiosity for a while anyway. So here's what a sine wave actually looks like. And you'll notice right away, it's a much more gentle thing. There's no sharp edges. And another thing, well, let's put it this way. Why do we use sine waves? Why are they so important? Well, when current flows in a wire, a magnetic field is created around the wire. When the current changes, the field changes. Well, with a sine wave, unlike a square wave, the current is always changing, so the field is always changing. And a changing field is part of what enables radio to work. So the sine wave is a fundamental aspect of radio. One other thing, that transformer out on the pole that feeds power to your house, It relies not on square waves, it relies on sine waves for efficient power transfer. So in a multitude of ways, from now on in radio, you are going to live your life concerned with sine waves. Now, a couple of little tidbits about the sine wave you should know. We talk about cycles, and in this case, when you look at this graph, the first cycle is going to start here. It'll rise to a certain polarity and voltage. It'll fall to zero. It'll reverse itself and fall back to zero. That is one cycle. We talk a lot about that. Now, getting back to the trig just for a minute, the trigonometric sine function, when used with a rotating vector, draws a circle. Circles have 360 degrees in them, at least as far as mathematics is concerned. Well, we kind of borrow that. So we say there's 360 degrees or divisions or sections in a cycle. 90 degrees is the first quarter of the cycle. If you add another 90 degrees, you're halfway through the cycle and you're at 180 degrees. Now, one thing you'll notice, I don't have this labeled as 360 degrees. We think of this as 0 degrees of the next cycle, but it's also 360 degrees of the previous cycle. Now, you don't have to concentrate on this very much. Just put it in the back of your mind that there's 360 degrees in a cycle. You won't use that for quite a while, but we'll come back to it. One thing you're going to use right away that you've got to get in your head right now is we say the frequency of a sine wave is a measure of how many times we go through a cycle in 1 second. This is super important to understand. Another thing, we used to say, or we used to describe how many cycles per second, or CPS, the frequency is of the signal we're looking at. That changed about 40 years ago. We now refer to a cycle per second as a hertz. So the 60 cycle per second power in your electrical outlet in your house is also a 60 hertz signal or power source. So just remember, cycle per second means hertz, and I doubt you'll hear cycle per second very often. The world has gone to the phrase hertz, but that's what hertz means. That is it for sine waves. It's that simple. You'll probably want to go through that section a few more times, but that's how simple sine waves are. Super important, but very simple. The problem is, now we've got to talk about the fact that in radio, and really all of science, if we're not dealing with a very, 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 very big number, we're dealing with a teeny, teeny, tiny number. That presents some challenges. So let's start with big numbers. You might once in a while use a common test tone of 1,000 hertz to test a microphone circuit. Or you might get on the 2-meter calling frequency, which is 146,520,000 hertz. But the thing is, nobody uses these terms. Nobody talks in terms of hertz. Also, notice hertz, hertz. I've introduced you to your first abbreviation. HZ means hertz. So getting back to what I was saying, how would we refer to these two frequencies? Well, the 1,000 hertz would be 1 kilohertz, and the 2-meter calling frequency, we usually refer to it in megahertz. That brings us to our first two prefixes we want to learn, the mega and the kilo. Pound these into your head. Mega means 1,000,000. Kilo means 1,000. There's one other big prefix you'll want to think about. We have a band at 23 centimeters, which is centered around the common frequency of 1296 megahertz, which is also 1.296 gigahertz. So also think in gigahertz. You want to learn these three abbreviations today, right away. Get them down so you're very comfortable with them. Oh, one more thing. The giga outside of science, a giga is a billion, but we never say a billion. Now there's some other bigger numbers or bigger abbreviations, but we don't deal with those in radio, so I'm going to keep going. You now have the three big abbreviations, or the three abbreviations for big numbers. What about small numbers? Well, we're going to have four items to remember now. The first is the milli. You can have milliamps or millivolts or milliwatts. You can have millihenries, probably have millifarads in capacitance as well. A milli is 1,000th of something, or 0.001 of something. Now, milli is not M-I-L-L-A, it's M-I-L-L-I. I was going to fix this, and then I thought, no, I'm going to show it to you, because it's a common mistake to say milli with an A. So always remember, I show you the wrong way, so don't do this. It's M-I-L-L-I. So 1 milli is 0.001 of something. So 10 milli is 0.01. 100 is 0.1. And 1,000 milli is 1. Now, a milli of something isn't small enough in most of electronics. So what about a milli of a milli? In other words, 1,000th of 1,000th. That would be a millionth, which we refer to as a micro. Now, if 1 micro is 0.000001, then say 100 would be 0.0001. You should know that we never or usually don't spell out micro. We use this little symbol, the mu. It looks like a U, and when I type something up, I usually just type U. But if you see that abbreviation, whether it's a real U or the mu, no matter what, that means micro. So these are the units you want to know. Notice there's milli, micro, nano, and pico. As I said, we have 7 items to remember, and these are their abbreviations. Do not ask me why kilo isn't a capital K, but it's not. So you want to be able to recognize all of these, but there's a couple of notes. The nano is just kind of like gone. We don't talk about nanos anymore. And early radio, up to about 50 years ago, they hadn't decided on pico. No one was using pico. Instead, for a pico, you used a micro. So you might find old capacitors that say like 39 mmF. Well, a modern capacitor would be 39 PF for picofarad. So if I did have a 1 nanofarad capacitor and it burned up or it failed and I wanted to buy a new one, you can't buy 1 nanofarads anymore. So what would I buy? Well, I could put in a 0.001 microfarad, or I could put in 1,000 picofarad. All three of those are the same capacitance value. And again, you're only going to see the nanofarad in antique equipment. Now, there are metric abbreviations for all of those other decimal places. In science and engineering, particularly radio, we don't bother with them. We don't remember them. We don't care about them. Once in a while, I will measure something in centimeters. Other than that, I never bother with any of them. We just don't use them. So if you can remember these 7, they're abbreviations, they're places, you got it made. That's all you've got to know. And any document you read, I believe you'll be covered and you'll understand the numerical value of whatever it is the author is talking about. These abbreviations are used when we measure frequency, power, capacitance, inductance, resistance, or current. They're also used for conductance and admittance, but we don't talk about those 2 factors in ham radio very often. They exist, but we really don't talk about them. That's it for this edition. I see I did it in 16 minutes. I'm kind of proud of that. I do encourage you to watch this over and over until you get every point that I've made. Once you're comfortable, move on to DCL 092. Thank you very much for watching. I wish you the best in your studies, and I hope this has helped a lot.